Our next speaker is Niyazi Gezer, and he is from Turkey, I believe, and he will be speaking on operator theoretic aspects of lattice pseudonorm. Sorry, what is on operator theoretic aspects of lattices and pseudonormed lattices. Thank you. Please proceed.
Thank you, sir. First of all, thank you for this opportunity. So this is a joint work with Nazife Erkurşun Özcan, and our title is on operator theoretical aspects of lattice pseudonormed lattices. So in my talk, so this is the table of contents. First, I will start with some motivations, and then I will give some preliminaries, and then I will continue with our theory. So the motivation, first of all, this work is about pseudonorms on vector lattices. Vector lattices are assumed to be Archimedean, and in the second part of my talk, the range of that pseudonorm will be a vector lattice. Such pseudonorms are called lattice-valued pseudonorms. First of all, let me start with some motivation. As I said, in this work, we are interested in lattice-valued pseudonorms on vector lattices. Our first reference is written by Aydın, Emelianov, Erkurşun Özcan, and Marabe. They published an article in 2018 about, they published an article with title Compact-like Operators in Lattice-normed Spaces. In this article, they used vector lattice-valued norms, and then they studied compact operators by using that type of norms. And again, our second main article is written by Aydın, Emelianov, Erkurşun Özcan, and Marabe. The title is Unbounded P convergence in lattice-normed vector lattices. Here again, this P is a lattice-valued norm. When the main book is written by COSAEF. This book is about lattice-normed spaces and dominated operators. And in 2017, Professor Ercan and his student Buran wrote an article titled Towards a Theory of Unbounded Locally Solid Real Spaces. In this article, they use pseudonorms, real-valued pseudonorms, and then they defined unbounded versions of those pseudonorms. And then they studied those properties. And another main reference is written by Gao and Santos. You already know this reference because it is mentioned a lot. In this paper, for example, they use seminorms in section 2.2 of this reference. They used seminorms to study properties of unbounded convergences. And another reference is written by Zanen. It is Real Spaces number 2. In this reference, you can find factorization theory of compact operators. And in addition, there's another reason. We have other projects. In one of our projects, we encountered pseudonorms to study Birkhoff averages. Because if you have a vector lattice and if you want to study Birkhoff averages, what you need is a norm. But in our case, we had a pseudonorm. So because of that reason, we studied pseudonorms. So I'm interested in a vector lattice together with one pseudonorm. If you consider a system of pseudonorms, then it is another business. So I'm interested in a vector lattice together with one pseudonorm. Related to this subject, we wrote 2 articles. One of them, the title of the first one is on some aspects of pseudonorm compact and Montel operators on locally solid vector lattices. In this first article, we use real-valued pseudonorms, and then we wrote another article on operator theoretical aspects of lattice pseudonorm lattices. In the second article, the range of the pseudonorm becomes a vector lattice itself. Now, let me start with an informal summary. As I said, I'm interested in vector lattices together with one pseudonorm. In our paper, for those for pseudonorms, we defined some properties. So we have different types of pseudonorms. For example, I will say that I will talk about bounded pseudonorms. They will be pseudonorms such that every pseudo-bounded set is order bounded. And then we defined almost bounded pseudonorms. They are those pseudonorms such that every almost pseudo-bounded set is order bounded. In this way, we defined various classes of pseudonorms. And from the classical theory, we have some other properties. For example, if closed unit ball of a pseudonorm is conditionally pseudonorm compact, then we say that that pseudonorm is of finite type. Or, for example, in the classical theory, we have order continuous norms. The same thing can be abstracted to the pseudonorm case. And in that case, we say that the pseudonorm is order continuous. In this way, we obtain different classes of pseudonorms. And so this table, I should say that this table is not complete, but it just reflects the idea. So this table is not a complete list, but reflects the main idea. In the case of Banach spaces, we do not have the notions of order bounded and almost order bounded sets. So if you work with pseudonorms on Banach spaces, then it is not possible to define this type of pseudonorms. And as you all know, by using a pseudonorm, by using a real valued pseudonorm, you can topologize this vector lattice, but that topology will be non-Hausdorff. And in our papers, instead of using non-Hausdorff topological results, we use comparative analysis of various versions of boundedness. What does it mean? It means that we compare different versions of bounded sets. We have almost order bounded sets. We have order bounded sets. We have pseudonorm bounded, non-bounded, etc. We compare them. So this is our technique. So this table is true for the real valued pseudonorm case. By using real valued pseudonorms, we study operators. And these are the classes of operators that we study. For example, we study pseudonorm compact operators. Their definitions are written here. Image of every pseudonorm bounded net has a pseudonorm convergent subnet. It is just the analog of conditional compact sets to this pseudonorm case. Please remember the definition of AM compact operator. We say that an operator is AM compact if T maps order interval T minus XX into the relatively compact sets. And we study order compact operators. They are those operators such that for every order bounded net, there's an order convergent subnet. And we then study semi-compact and pseudo-semi-compact operators. For example, in the pseudo-semi-compact case, images of their definition is as follows. Images of pseudo-bounded sets are almost pseudo-bounded. And similarly, we have the versions for M-weakly compact and L-weakly compact operators. Now, depending on, so in order to define an operator, you need domain and range. Obviously, they are vector lattices in our case. And in the domain and range, we have pseudonorms. So depending on the types of pseudonorms and depending on the type of operator, we have many relationships. On some spaces, for example, semi-compact operators become AM compact operators in the pseudo versions. And in some spaces, semi-compact becomes compact, etc. And in our paper, we try to list all of these properties. And in the vector valued pseudonorm case, we have these versions of pseudonorms. In this case, it is E-valued. I'm talking about E-valued pseudonorms. For example, we say that an E-valued pseudonorm is bounded if every pseudo-bounded set is order bounded, and so on. So these are the definitions. These definitions, first of all, abstract from the real case. So the real valued case provides examples for the E-valued pseudonorms. And we have other definitions. And in in both real and E-valued case, we have the unbounded, we have the notion of unbounded pseudonorms. I will talk about it. And again, in the E-valued case, we talk about operators. In this case, we have again pseudonorm compact, pseudo semi-compact operators, and so on. In addition, in the E-valued case, we talk about continuous BB-bounded and MB-bounded operators. So please remember from the theory of locally solid spaces that an operator is BB-bounded if it maps bounded, all bounded zero neighborhoods of that space into the bounded set. In that case, we say that T is BB-bounded. But in my case, in this case, we don't have topology. We don't work with topology. But it is again possible to define it. A BB-bounded operator will be just an operator which maps pseudo-bounded sets into pseudo-bounded sets. And similarly, the same is true for MB-bounded. For the MB-bounded case, this MB-bounded, this notion is defined on locally solid spaces for operators. And in our case, we don't have neighborhoods. Maybe we have neighborhoods, but we, in our paper, we don't work with neighborhoods. Anyways, it is possible to define operator in this way. So let me start with the preliminaries. So let X be an Archimedean vector lattice. Please remember that a real valued, a non-negative real valued function is said to be a pseudonorm on X if it satisfies this inequality. And limit of rho theta X goes to 0 as theta goes to 0. This definition can be found in the book of Ali Prantes. If furthermore, it satisfies this scalar property, then we say that it is a seminorm, and a seminorm is of course a norm if this zero condition holds. And a pseudonorm is Ries pseudonorm if it respects absolute value. That is absolute value of X less than or equal to absolute value of Y implies that rho X is less than or equal to rho Y. So how do we obtain pseudonorms? There are many techniques. It is clear that a seminorm is a pseudonorm, a norm is a pseudonorm, etc. If you have a seminorm, then the expressions of this type, rho divided by 1 plus rho, is a pseudonorm, but not a seminorm in general. Moreover, you can take their convex combinations. It will be again a pseudonorm. The Ries property fails, but in our the Ries pseudonorm property may fail, but in our paper we always discuss this Ries pseudonorm property separately. Okay. And moreover, if you have a functional, then it is possible to create a seminorm on the space, and in different ways. If that functional is order bounded, then you can use this formula to obtain a Ries seminorm on X. And it's also clear that not every pseudonorm is a vector lattice norm. Okay, we have this example. So this example shows us the ways to create pseudonorms. So for given a pseudonorm, we can define a neighborhood in this way. It is the set of those x's for which rho x is less than or equal to 1. It is the closed unit ball of that pseudonorm. Now the problem is the following. The problem is that scalar multiplication is not continuous with respect to topology of rho. So the problem is this. I mean, so if you multiply this neighborhood U rho by epsilon, then it may contain some elements. It may contain some elements such that pseudonorm of that element is less than X. This may fail. Okay, so this may fail. An example is written here. Just consider this pseudonorm and take these numbers. If X belongs to this epsilon times that neighborhood, but its rho value will be bigger than epsilon. Okay. Now let me give you some. Let me remind you some auxiliary definitions. We say that a non-empty subset is pseudo-bounded if rho B is bounded. And it is easy to see that if rho is a Rees pseudonorm, then every order bounded set is pseudo-bounded. And a non-empty subset B is said to be almost pseudo-bounded if for every epsilon there's an order interval such that that set can be covered by an order interval plus epsilon times u rho. Okay. This is just the version of almost ordered bounded set into the pseudonorm case. So there are some simple implications. For example, if rho is a Rees pseudonorm and if B is order bounded, then B is almost pseudo-bounded. Every almost pseudo-bounded set is pseudo-bounded. And if rho is a Rees seminorm, then B is almost pseudo-bounded if and only if the usual condition for almost order bounded sets is true. I should say that here I'm defining notions for the pseudonorm case because I work in that generality. But here, for example, I assume that rho is a Rees seminorm. Even in this case, I don't write seminorm bounded. I use the definition given in the paper, okay? So, and I should say one more thing. Here, the proof of this proposition is similar to the proof given in the book of Zane. But I think this is true for the seminorm case. I couldn't generalize it to the pseudonorm case. Okay. Anyway, so I start with, this is a definition. So I say that a pseudonorm is a bounded pseudonorm if every pseudo-bounded set is order bounded. And I say that rho is almost bounded pseudonorm if every almost pseudo-bounded set is order bounded. And I say that rho is coarsely almost bounded pseudonorm if X is normed and it is a normed lattice, and every almost order bounded subset is almost pseudo-bounded. And similarly, I say that rho is semi-bounded pseudonorm if every pseudo-bounded set is almost pseudo-bounded. So the other implications, for example, let me start with the first one. I said it, just in the vector lattice, consider a non-vector lattice. If a set is order bounded, then it is, of course, non-bounded. Now I define, in the pseudonorm case, I define the reverse direction. I say that rho is bounded pseudonorm if every pseudo-bounded set is order bounded. In each case, I go in the different direction. In that way, I define these pseudonorms. And then we say that, and then a norm or semi-norm on X is said to satisfy some properties given in this definition if it is regarded as a pseudonorm, which is a norm or semi-norm, respectively, satisfying these properties. So, okay, it is clear. So I can say that a norm is a bounded pseudonorm, and a semi-norm is a bounded pseudonorm, etc. So the examples, the main example, come from AM spaces with a strong norm unit. So, example, recall that an element E in a normed vector lattice, a positive element E in a normed vector lattice is said to be strong norm unit if its norm is 1. And if X is less than 1 in norm, then this implies that X is less than E in absolute value. Now, it is given in Zahnen's book that for AM spaces, every order bounded set is non-bounded. And the same is true for almost order bounded sets. So, for example, if you take an AM space with a strong norm unit, then the norm itself is almost bounded and semi-bounded with respect to the previous definition. And a semi-bounded pseudonorm can be neither bounded nor almost bounded. One can find examples. And if, for example, if you have a pseudonorm such that its unit pole agrees with norm, then we say that rho is coarsely almost bounded pseudonorm. And in this case, if you just consider norm, then it will be coarsely almost bounded norm. And it's possible to obtain pseudonorms which pseudonorms satisfying this property, which are not norms. And in this way, we obtain some propositions. For example, a pseudonorm is bounded if every pseudo-bounded subset of the positive cone is order bounded. You can work with positive cones by using this RIS pseudonorm condition. The same is true for other notions. And you can consider convex combinations of these type of norms. The collection of all bounded pseudonorms is a convex set. Similarly, the collection of all finite type seminorms and the collection of all order continuous seminorms are convex sets. And the collection of all almost bounded pseudonorms is not closed under convex combinations. And the unbounded version, the following result is taken from the work of Ercan and Vural. It provides an analytic technique to derive RIS pseudonorm from a RIS seminorm. The resulting RIS pseudonorm is known to have topological relationships with the initial RIS seminorm. So how do we obtain it? Suppose that rho is given, it is a RIS seminorm on vector lattice X, then you just define a new pseudonorm, rho sub u, in this way, then it becomes a RIS pseudonorm. So this lemma is taken from Ercan and Vural. Then we can just do some comparisons. For example, say this is unbounded pseudonorm, rho u. If rho u is a bounded pseudonorm, then rho is a bounded seminorm. If rho u is almost bounded pseudonorm, then rho is almost bounded seminorm. In this way, we can study the relations. And we have other version. Again, in the same reference, they define these unbounded pseudonorms for subsets of the positive cone. So in this case, we have again pseudonorms, different pseudonorms, and we have these relationships. For example, if for one element, if rho u is bounded pseudonorm, then rho sub big U is bounded pseudonorm, and so on. Okay, so the main topic is the operator theory. So we define pseudonorm compact operators in this way. An operator is between two pseudonorm lattices is said to be pseudonorm compact if it maps every pseudo-bounded net X alpha into a subnet such that that subnet, if T maps every net into a net such that in the image there is a subnet that is convergent with respect to pseudonorm. This is the net characterization of compact operator. And we recall that an operator is AM compact if and only if it maps order interval into relatively compact set. Now we have theorem. Let rho be a bounded pseudonorm on a Banach lattice, and let Y be a normed vector lattice. If an operator is AM compact, then T is pseudonorm compact with respect to rho and the norm on Y. And in another proposition, let rho be RIS pseudonorm on a Banach lattice. Let Y be a normed lattice. If an operator is pseudonorm compact with respect to rho and norm of Y, then T is AM compact. So as you see, by changing the properties of the pseudonorms on domain and the range, we study the relationship between different classes of operators. This is the idea. And the proofs are not hard. The longest proof is 2 paragraphs. But if all of them are written, then it becomes interesting. Another proposition, suppose that T is a pseudonorm compact operator between 2 semi-normed vector lattices, and let rho and V are be positive elements. If rho U is a bounded pseudonorm on X, then T is pseudonorm compact with respect to unbounded pseudonorms. And let X be an AM space with a strong norm unit. F is in the dual of X, and just consider this pseudonorm. And let Y be a Banach lattice. If T is compact, then T is pseudonorm compact with respect to these pseudonorms. And we have a corollary. Suppose that X is an order continuous Banach lattice, and U and V are from the positive cone. Let rho be RIS seminorm such that rho is coarser than the norm, and that rho U is bounded. If an operator is AM compact, then T is pseudonorm compact with respect to these unbounded pseudonorms. Here, this definition for coarser and finer comes from topology. It comes from topology in the usual way. So, and then we study order compact operators, and operator T between two vector lattices is said to be order compact if it maps, if for every order bounded net X alpha, there is a subnet and Y such that Tx alpha beta converges to Y in O. This is the definition of order compact operators. Recently, we published an article related to order compact operators. It is written in the third item. So why is it related? Under some conditions, if an operator is order compact, then it becomes pseudonorm compact. The condition is written here. If the pseudonorm on the domain is bounded and on the range, the pseudonorm is order continuous. And if in the domain rho is Ries pseudonorm and the pseudonorm on the range has the subnet property, then if T is pseudonorm compact, then T is order compact. So in this way, we study. Now let me skip these parts because I want to talk about lattice pseudonorm lattices. In the lattice pseudonorm lattice, first of all, what is it? It is, we start with, and again, Archimedean vector lattice, and then we take another vector lattice. We say that rho is an E-valued pseudonorm on X if it is monotone, if it satisfies this property, and if it satisfies this property, limit of rho, theta, and X goes to 0 in order of E for all X, and theta n goes to 0. And if rho is monotone, that is this Ries condition holds, then we say that rho is an E-valued Ries pseudonorm on X. Pardon me. So a lattice-normed vector lattice, sometimes denoted by LNVL, can be regarded as a lattice pseudonormed lattice because every lattice norm is a lattice valued pseudonorm. Okay. And if this example is rather important, if you have a vector lattice, then of course we have an absolute value on it. Now this triple X, absolute value X, is a lattice pseudonorm lattice. This is an important example, I guess. And similar to the real valued version, in the E-valued version, we have the same techniques to create pseudonorms. You can consider their convex combinations, and you can consider functionals. In the E-valued version, we say that a subset is pseudo-bounded if rho B is an order-bounded set in E, and a subset B is said to be almost pseudo-bounded if this condition holds. And we say that rho is relatively compact if it satisfies the condition of conditional compactness for the pseudonorm in this way. And again, similar to the previous version, we have some results. For example, a set B is almost pseudo-bounded if and only if its absolute value in the positive con is almost pseudo-bounded. And in the E-valued case, we have the versions of those types of pseudonorms. We use the same things, and they are almost the same. For example, we say that E-valued pseudonorm is bounded or almost pseudo-bounded if it satisfies certain properties. And this example, as I said, is important because if you consider vector lattice together with absolute value, then it becomes a bounded pseudonorm. So this shows that my definition is natural because absolute value satisfies that definition. And again, AM spaces with strong norm units provides examples for the real case. Therefore, they provide examples for the vector valued case. And let me just jump to this definition. In the vector valued pseudonorm case, it is possible to define BB bounded and MB bounded operators. But as I said, this is not non-topological. For example, here we have a theorem. Say we are given two lattice pseudonorm lattices where rho is a bounded pseudonorm. The first, in the domain, rho is bounded pseudonorm. If an operator is order bounded, then T is BB bounded with respect to the norm and rho prime. In particular, this is the case if one considers this space and this space. So if one considers X absolute value X. And in the vector valued case, we have again different versions of operators. We have pseudonorm compact, pseudo semi-compact, order AM compact, and pseudo AM compact operators. These two things are new. We say that T is order AM compact if the images of order bounded sets under T are rho prime relatively compact. And we say that T is pseudo-bounded, pseudo-AM compact if the image of pseudo-bounded sets is rho prime relatively compact. In the real valued case, we don't have these two types of operators. For example, we have, as a demonstration, we have this theorem. Say we are given two lattice pseudonorm lattices such that rho is bounded E-valued pseudonorm. If an operator is order AM compact, then T is both pseudonorm compact and BB bounded. And I think my time is up. So let me show you one more slide. What about the unbounded versions? It is possible to, again, in the vector valued case, it is possible to define unbounded pseudonorms by using the same formula. And in this case, we have this theorem. For example, let X rho E be such that rho is an E-valued seminorm on X, that U be positive, and define an unbounded version of that seminorm in this by using this formula. This is an E-valued pseudonorm on X. The identity operator is both BB bounded and MB bounded. And we have some other results. So for the references, as I said, our main reference is this paper. It is written by Professor Emelyanov and Aydın and Erkuşnurcan and Marabe. And this is another main reference. It is written by Ercan and Vural. And further information about BB bounded and MB bounded operators can be found in the paper of Trotsky. This paper. And that's all. Thank you.
Thank you for your very interesting talk. Are there questions for the speaker? Sure, there must be some questions. I think you stunned the audience.
Yeah, yes.
Well, since they haven't got any questions to ask you, thank you very much again. It was very interesting. And that concludes this afternoon's session. Thank you very much, and we will see you all tomorrow.
Thank you. Thank you.